Midterm review problem number 5. It's another system of connected objects. We're going to use Newton's laws, but our shortcut to find the acceleration of the system, and then we'll answer some other questions like what are the tension forces in the two strings, and what's going to happen if we turn off the friction in the problem. So the setup is that there are 3 masses and they're connected via strings over pulleys, and the numbers you all are given in WebAssign are different, but I think for all of you it's going to be the case that mass 1 is greater than mass 3. If that's not the case for some reason, then you'll have to flip a few of the steps we do. But kind of the first thing to look for in this problem is noticing which of these 2 masses is larger, because that's going to determine which way the system moves. So if mass 1 is larger, that means the gravity force on mass 1 is going to be larger than the gravity force on mass 3, and so mass 1 is going to move down, mass 2 will move to the left, and mass 3 will move up. So right off the bat, once I look at the numbers I'm given, that will allow me to determine which way the system is moving. Okay, so now let's figure out the acceleration for the problem. If you really like doing lots and lots of algebra, you can write separate free body diagrams for each object and all the Newton's second law equations and solve that system of 3 equations. It takes a long time, but I'm going to use the shorter method where we say that the acceleration of the system is the sum of the net external forces on the system divided by the total mass. And remember, we have positive signs for the forces that make the system speed up and negative signs for the forces that make the system slow down. And in this scenario, if we use a little common sense, the force that's making everything go, or everything speed up, is the gravity force on M1. M1 is the bigger mass here, so the system is going to move in the direction I drew, and the gravity force on mass 1 is really the driving force that makes everything speed up, that makes it accelerate. So the gravity force on mass 1 is just M1g. I'll give that a positive sign. Now mass 3 has a gravity force on it, but that is not helping the system speed up. It's fighting against that gravity force from M1. So I'm going to do minus M3g. The gravity force on mass 2 is kind of irrelevant because it's perpendicular to the motion of mass 2. But there is a friction force, and friction forces always slow things down. You'll always get a minus sign in these types of problems for the friction force. And we draw on our past experience solving friction problems to write down the friction force on mass 2. It's mu times the normal force. There's mu, the coefficient of kinetic friction for mass 2. And there's the normal force on mass 2, which, because it's horizontal, equals its weight. And that's it. Those are the 3 forces involved, and we divide by the total mass of the system. So it's pretty remarkable, I guess, that we can write down this answer in just a minute or so, as opposed to spending half an hour trying to do all the algebra if we went through the full Newton's second law procedure. Of course, if you want to do that whole procedure, feel free, but know that this way is a lot faster. Okay, so that was the first question, to find the acceleration. And now the problem also asks you to find the tension in each of the strings. So there's two strings. There's the one over here on the left, and there's the string on the right. Because that tension force was internal to the system of the three objects and the two springs, we couldn't find it earlier. So now we need to find this tension force by considering some systems or subsystems where the tension force is external to that system. And the simplest way to do that is to consider mass 1 as its own system, do a little free body Newton's second law analysis for that. And that'll help us find the tension in the left string. Then we'll do mass 3 as its own system, Newton's second law process, and find the tension in the right string. Okay, so to do the left string, I'll draw a free body diagram for M1. This is a pretty simple free body diagram. It has the gravity force of the Earth on mass 1, and it has the tension force of the string. Actually, I'm going to use a better letter. Tension force of the left string on mass 1. I'll use L for left string because we've also got a string on the right. So Newton's second law in the y direction says that tension force minus gravity force equals M1 A1. And we've got T L equals gravity force, that's M1G plus M1A1. And now there's just one subtle thing to keep in mind. This is the trickiest part of this problem. M1 is accelerating downward. So this acceleration has a sign in it. This acceleration equals minus A, the value we found in the first part of the problem. This A is essentially a magnitude. This A1 for mass 1 carries a direction. And because mass 1 is moving down, A1 equals minus A. So that means that the tension in the left string, I'll drop the subscript 1, equals M1G minus M1A, where A is the value we found up here. Let's do the same thing for the right string. We'll do a free body diagram for M3. This looks pretty much the same. We've got the gravity force of the Earth on mass 3. We've got the tension force from the right string, R, on mass 3. We do Newton's second law in the y direction. That gives us tension minus gravity force equals M3A3. Tension force equals M3G plus M3A3. And this time we note acceleration of mass 3 is upward. So it equals positive this value A. And that means that the tension in the right string is M3G plus M3A. If there were no friction, how would these tension forces change? Well, let's look at these expressions. You can see that these tension forces depend on the weight of those objects. That's not affected by friction. And they also depend on this acceleration value, which is affected by friction. So imagine that there's no friction and this term disappears. Because this term is subtracted, that means the acceleration would be faster. It'd be a larger value, which makes sense. If there's no friction slowing the system down, it's going to accelerate faster. So A will have a larger value, which means that the tension in the left string will be smaller, because A has a bigger value and this term is getting subtracted, and the tension in the right string is going to be bigger, because A gets bigger and this term gets added. All right, so in terms of exam questions, I'll tell you right now that I am not likely to give you this exact setup in a system of connected objects kind of question. I may have a variation where there's some number of objects and some of them might be on slopes, some might have friction. So in problem 4, we had 2 objects, one was on a slope, they both had friction. In problem 5, there's 3 objects. One of them is on a flat surface with friction, 2 are going vertically. So there's lots of possible configurations. Just keep in mind that you know how to do all the sub-problems. All these terms in the acceleration are a sub-problem. If an object is hanging vertically, you know that the force on it is the weight. If there's friction, you know how to calculate that, whether it's on a flat surface or a tilted surface. If there's a gravity force on a tilted surface, you know how to calculate that. So you can just put together all these results that you've learned over the past few weeks and combine them in any sort of system of connected objects that you might encounter.